In this lecture, we are going to discuss binary search. It is one of the key searching techniques in design analysis of algorithm, and it is an efficient searching technique. The input for binary search, it should be sorted input only. Here the search will happen based on the middle value, which we call it as mid. We need 3 pointers to perform binary search: left, middle and right. We'll call it as L, mid and R. So this is how we should compute the mid value. It is L plus R divided by 2. We have to take the floor of that. And the time complexity of binary search is order of log n. This is because of reduction in search space by half after every iteration. There are 3 cases in binary search. The very first case is if data equals to A of mid. That is, the element that we are searching is present at the middle itself. So this is the condition. L, M, R. So this is left pointer, this is right pointer, and this is M. If A of mid equals to data, then we can conclude that the element is found. Okay. The next condition is if data is less than A of mid. Okay. So what will happen here is that time you have to make R equals to mid minus 1. I'll tell you. So this is L, this is M, and this is R. Okay. The data is less than A of mid. What do you mean by that? So this is the place where the data is present. Yes. So that time you have to make R as mid minus 1. So now R will come here, which is R will become what? Mid minus 1. So now this is the search space. This is the search space for that element. What is the third case? If data is greater than A of mid. If that is the case, then L should be mid plus 1. So what is the case here? So this is the search space. Now L will become here. L equals to mid plus 1. Okay, you have to add plus 1 to mid. So this is the search space when data is greater than A of mid. So these are the 3 cases for your binary search. Now let us discuss this with an example. So I'm taking the input. The input should be a sorted input. So I'm taking 3, 4, 7, 10 and 12. You can take any sorted input. Okay. What is n here? N is 1, 2, 3, 4, 5. Just count the number of elements, that is n. Okay. What is the data to be searched? You have to, let us assume the data to be searched is 10. Okay. Now the very first iteration is we have to find mid, right? Make 3 things: L, R and mid. Okay. L, R and mid. Now we'll work for every iteration 3, 4, 7, 10, 12. And make it as A of 0, A of 1, 2, 3, 4. So these are the indices. At the very first iteration, this will be my L and this is my R. 0 is my L and 4 is my R. Now we need to find the mid. So 0, 4. What is the middle value? 0 plus 4. Just now we saw the formula, right? Here it is L plus R divided by 2. I'll write it here. Mid equals to floor of L plus R divided by 2. What is the middle value? 2. What is A of 2? It is 7. Is A of 2 equals to the data that we are looking for? No. A of 2 is not equal to 10. Okay. Then else, if what is the condition? We have to check whether the data that we are looking for is less than A of mid. Okay. The data to be searched is 10. A of mid is 7. So this condition also fails. Both the conditions, okay, fails. What is the third condition? Else if that is the data is greater than A of mid. So if that is the case, what we have to do? We have to make L as mid plus 1. What is the current value of L? It is 0, but we have to make it as mid plus 1. What is the current value of mid? It is 2. 2 plus 1, 3. Now, the search space will become, remember, 3, 4, 7, 10, 12. Okay, this is my first iteration and this is my second iteration. Okay, so now left will become 3, 0, 1, 2, 3, 4. This is my left pointer. Yes or no? This is my left pointer, and the right remains the same. Now what is the iteration? Now L is 3. What is R? It is 4. 3 plus 4, 7 by 2, it is 3.5. Okay, we have to take the floor, then middle value is 3. Now what we have to do? Check whether A of mid is, check whether data equals to A of mid. What is the data here? It is 10. A of mid is 3. A of mid is, what is there in A of 3? It is 10. Now the search is successful. Now the search is what? Successful, and element is found. So this is how the binary search works. So let us discuss the pseudocode for this binary search. So as we discussed, there are 3 things that we need to pass on. One is the array and the number of elements and the data to be searched. So as we saw in the example, L should be the 0th index and R should be the n minus 1th index. So L is 0 and R equals to n minus 1, and we keep doing all these things until L is less than or equal to R. Okay, if this condition fails, then it will come out of the while loop. So we have to compute the mid as we discussed, and we have to check all these 3 conditions. If data equals to A of mid, we have to return the mid and the search is successful. And if else if we have to check whether the data is present at is less than A of mid, then you have to bring your right pointer in such a way it is mid minus 1, else you have to make the left pointer as mid plus 1. So this is a pseudocode for this binary search. Now let us discuss the time complexity of binary search. So what is n here? In our example, n is 5. Okay, n is 5. In the initial iteration, the very first iteration, or after completing the first iteration, the search space has been reduced to half. Okay, now we conclude that this was the search space, and we are no more going to bother about this one. Half of the search space has been reduced. Yes or no? Again, in the next iteration, in this we are going to consider only half, and we are going to ignore this part. After every iteration, the search space is getting reduced. By this, the number of comparisons also getting reduced. Search space reduction leads to less number of comparisons. How come? So you're just making half of the search space. In that, we are just going to make few comparisons. Assume n equals to 5. How come it is log n? What is log 5? log5 is 2.33 approximately. If you look at our example, NS5, hardly we made how many comparisons? Approximately 2 comparisons. In our example, how many comparisons? Approximately. Okay. So we'll discuss the time complexity. Best case, the number of comparisons is order of 1, because what is best case? A of med equals to data just by 1 comparison. Worst case, order of log n. How come? The search space reduced by half after every iteration. Yes, that could be the worst case. Average case, similarly, at least it should make log n comparisons even after the search space reduction. So this is your time complexity for binary search. Thanks for watching this video.